recording. Okay, so who else doesn't manage to install the package at all? Anyone else didn't it didn't install at all, Sam?
I have some problems during installing the package also.
Which link did you use to install? Did you use Conda or pip or you used GitHub?
No, Conda.
Conda, okay, and it told you some of the dependencies doesn't resolve, or what happened?
Some parts of the package were not available.
Not available.
Yeah.
Okay.
Maybe I have to try it again.
Okay, so you can take a print screen and send it to me. Okay, so
Of course.
okay, do you all know now where is the colab link or the colab code or not?
Yes.
Yes.
You mean the last one that you sent?
Yeah, the one.
Yes, yes.
Okay, I will put it again in case you guys don't know. Okay, so can you open it? I put the link right now on the Slack group, and you can go on all and open it and start the installation at the very beginning of the code. So all of these packages at the beginning is actually what you install when you install Hapi. So it is mainly based on GDAL and NumPy, and all of these other libraries are they do some of GIS stuff. This Affine and Fiona projection and raster.io and stat models. Raster.io is dealing with rasters, stat models for some statistical analysis. And the optimization algorithm that I did is this one. It's called Oasis, and netcdf for reading and converting netcdf files. And ECMWF is the one that's downloading from the server of ECMW. So yeah, when you install Hapi using Conda or pip or from GitHub, it is doing exactly the same thing. So if your environment, the Python environment, has any library that has a conflict with any of those, you are going to have a problem, and Conda is going to try to resolve it using older version of any of these libraries. If you install from bib doesn't resolve any conflict, so it's going to give you error. So there is a where it is, yeah. The data is in Google Drive, so you should copy it to your Google Drive. All of you has Google Drive account?
Yes.
Yes.
Okay,
Yes.
I guess I have already put the link to the data, right? Yeah, it is in the data channel in Slack, and it's already shared by. Oh, not this one. It's compressed. So did it finish installing?
Yes.
Okay, so try to run the next two blocks. The first one is importing Hapi. So if you have a problem when you run it, that means the installation didn't go as planned, but I guess it's going to be installed. And run also the third block, and that's what's going to link Colab with your Google Drive. And it's going to open another window, and it will give you a code. You have to copy it and paste it in the box that's going to open. Did it open with you? Did you manage to run till the third block or not?
Yeah.
Yeah.
Okay, so please wait, I will give you the link to the Google Drive. Yes, here it is. Okay. And I will put it here in the chat. Yeah, now you have it. So go copy it and put it in your Google Drive, and in the fourth block, that's where we will tell this Python in Colab where the data are. I don't know if you run it like this. I don't know if it is going to link to my Google Drive or not. Can you try?
Is it possible to share your screen with us?
Yeah, sorry.
Maybe. Thank you.
Yes. Here.
Yesterday, I copied that that notebook actually, and yes, it let me work. It take a little bit of time to install all the libraries and some of the process, but for me it ran good in Colab.
So you tried it yesterday. Good, good. So yeah, you see here is like, yeah, installing the package is, yeah, it's not a rocket science. So you just has to put this, and when you install it in your machine, probably because you have already installed some other Python packages, you might have some conflict with these packages that you already installed. But when you create like a new environment and you start with these packages, yeah, you will have nothing to conflict with, and you will not have any problems at all. So you just leave it for 10 minutes, and you see here, it found some conflict with the version, I guess, with matplotlib, and it resolves the problem. So you don't have to do anything. And yeah, so if this block run already, so it is importing some modules from inside Hapi. So that means it is working. And yeah, so this part is going to ask to connect with Google Drive, and that's actually what you do when you are in your computer, and you tell when you are going to read any data, you put the path. And here, when I did this mounting and I opened another link and it gave me the code that I have to put here, it already got inside the browser, and that's my Google Drive. So here is the file that I shared with you. So did you already all run the fourth block?
Yes.
And okay, so all of you or the others? Did it work for the others or not?
Yeah, it works.
Oh, it works. Okay,
Yeah.
so can you please tell me so I have to proceed and not wait? Okay, so this part, what I showed yesterday, it is the one that's going to read. Yeah, these are where all the data exists. So if you browse in here in the left panel, Coelho. Okay, so someone is trying to get in. Okay, so this version of, yes. Okay. Yeah, so yeah, run. You can go on and run all the blocks, and I will go with you on, and I will go on with you and explain block by block. So yeah, so this is just links. You are defining the links where are precipitation, where evapotranspiration, and as I said, it is already here in the left. If you browse in the left panel, you will find all the data. So here, meteorological data, here where there is for 1000, here it is. And yeah, every file of those has all. So it's going to take time to open because it has like 1000 raster inside it. So each one of those has the same number of rasters. So the time series that I defined here from the beginning of 2019 till the end of 2011 is the time series. So when you run this, so basically we here are instantiating the object catchment and we called it Coelho. So the good thing here in Colab is that it gives you, like, if you see this definition that goes up when I put a cursor on top of the object, so that's the definition inside, and in top here it defines what are the inputs. And this block is the block that's going to start reading. So this one, it might take some time. So if I run it here as well on my laptop, yeah, it is reading a lot of files, so it might take some time. But in your computer, it's not going to take any time. So here, what I call it meteorological data, all. So it's not going to take that much time. So yeah, rainfall rate, temperature, and yeah. So you see here, if you run it in your laptop, it's going to take a fraction of a second. And so is it taking that long time with you to read the meteorological data?
Yes.
Yes.
Yeah.
Yeah,
Seems to take longer in Colab than in Jupyter.
in Jupyter longer.
No, in Colab it takes longer.
Yeah, and it also it depends on your internet connection. So yesterday when I was checking it, like very late at night, it was very fast. But okay, so I will, yeah, I'm sharing my screen. So every method inside Hapi, when it is being done, it will give you a message. So here, every message of those is corresponding to every method of above here. So when it finished runs a model, it's going to give you this message. And yeah, the next block is this gauge block, reading the gauge data. We read it to you have to have a table, and this table I showed yesterday where it have ID for each gauge and X and Y, and if you want to associate any other thing like the factors that I talked about yesterday, and you have to give it the flow accumulation raster, pass to the flow accumulation raster. in order to locate this xy for each gauge, and this method is going to calculate, yeah, this xy is located in this cell, so I have to extract the discharge for this gauge from this cell in the array. And yeah, so yeah, here is where you run the model, and oh, this one is not working. So yeah, the colab is for those who didn't manage to install the package, but the others can go on with their laptop. So yeah, now I run it again here. Did you copy the files to your Google Drive, or you are reading it from my Google Drive?
I did copy to my Google Drive.
Okay. Oh my God. So yeah, here also the running, because Quello is small, not very small. So if we, yeah, if I add it here and not here. So here the running is already finished, and if I add it here, so Quello dot Q total, and this is a 4D array. So if I said everything, so the first two indices are x and y, and the third indices is the time. So if I press like this, it will give me an array, and if by dot shape, number is not defined, so as nb, so it is 13 rows and 14 columns. Those numbers definitely they will differ from case study to other case study, but yeah, times so the time depending on how big is your catchment. So and we can, so it is 13 rows and 14 column, and the length of the time series is almost 1100. So the first part of the model where it is calculating the vertical movement of the water, running the lambda model, it is making the calculation by this number. Okay, and then it proceeds with the distributed routing. So yeah, here this block is calculating the performance. So inside Hapi there is a module for it has a lot of error calculation. So yeah, all of these error I put them here, as you see here. So these are not very good metrics, but as I said, this model is not yet calibrated. So yeah, for other model, in order to get to this stage where you have a comparable, you can compare the hydrograph with the observed hydrograph, you might take weeks or months. But yeah, as I said, this is a just initialization or as an initial step we take to the calibration.
I'm sorry, Joe just text me to the
To
Zoom. Joel,
Oh yeah, here.
Dr. Colin, yeah.
Yeah. And yeah. So yeah, so here these are the performance metrics, and yeah, so here in this gauge, so you choose whatever gauge you want to plot. So because in the gauge table that I have, I can show it here. So Quello.gauge. table and gauges. So you have to write it quickly. So it is a table, and as I said, so it has to has the first column as an ID, and this ID has to be unique number. So no two gauges has the same ID. This name is yeah, whatever you want, and X and Y. So this coordinates has the same has the same projection as the DM, and yeah, this factor that I calculated based on the original area over the area that that's calculated after resampling the DM. I passed it here to the calculation of the error. So if I remove this and I calculate it, the calculation is going to errors are going to be different. But so as you see here, this extract discharge, it's going to work if you didn't provide any parameter. But when I can also plot this one. So this this ratio or this factor is the one here, this area ratio. So I have six gauges. So you have to provide as number of factor as the gauges, as in and it is a list. So if I put this like this, so it is a list of number. So it is a list of numbers. Okay. Yeah. So after you do the calculate, you run this extract charge. It's going to create this dictionary inside the main object. So it's called metrics. So this metrics here it is. So it has root mean square, Nash subcliffe, Nash high flow, Kling-Gupta water balance, this Pearson correlation, and coefficient of determination. So whatever, if you have other metrics or other equation you want to calculate it based on to compare between the observed and the simulated discharge, you can use it here. So what else? So this object Coelho, I said it has everything. So if you put star dot, it's just finished reading the info. Okay, so yeah, here in Python, if you put dot, you have access to all the method and all the attributes inside any object. So you can actually browse to get whatever you want. So this, yeah, and it is it has this is a type instance. So this accumulation value, this is an array. It has the flow accumulation. Catchment area is a catchment area, and so Lambda model is a model, the one that we the HBP that I talked about, and that's what we passed to inside to make the calculation. So here are these are the result. So Q lower zone is the result, is the lower. So it's an array of the base flow, and where else? And this is lower zone translated is the lower zone discharge after it is after it follows the river network. Q out is the output at the outlet of the catchment. And what else? Total is this is an array. This is a 3D array. So X and Y for each time step. Yeah. So you can play with it like this till you. Yeah, all the attributes are stored in this Coelho.
Yeah, maybe Mustafa, hi, how are you doing? I arrived
Good.
a few minutes ago. And on this 3D array of the output, which I imagine that contains the location of each one of the surface runoff, if we can interpret it like that, is the case that is a NumPy array whereby you could The first one is time, and the X, Y are the coordinates of the cells, the location of the cell, because I know that it's not latitude and longitude. So
It
if you
is
say,
it is NumPy array, so it doesn't have anything. So it is just array. It's it has
okay, yeah, but then so the X, Y, what is the X? The X, Y are the coordinates of your grid where
yes.
you locate it. But since you have a mask that is associated to the exactly, can you do the shape and tell us what are the X and Y and the yeah here exactly?
So this is the time.
What's time? The third variable, the third dimension is the time. The first two
Yes. X
are
and Y.
the X and Y. So the X will correspond to the cells in a 13 by 14 matrix, but some of the 13 are empty because you have the mask is not all the 13 by 40 because it's not completely square, right?
It is completely square.
So it is completely square, but means you don't have flows in places where the basin doesn't have values,
Yeah,
right?
exactly. So let me plot some
So
of
can
the
you show
images.
one in time? Just make one plot with one in time here. Just
Okay, so it
with the,
yeah,
any time
here
steps.
it is. So those are 13 row and 14 column. So in this area, we don't do any calculation where where uh, where you have no data value in your DM. So you have masked your catchment at this size. So we don't do calculation outside. And in this cells, you have the no data value that's stored in your DM.
Yeah, precisely. So that was what I think is you have many empty cells, if you want to call it like that. And the third dimension is the time.
Yeah.
And yeah, so if you want to have a time series, you have to find out which ones are the cells that has values. But I was wondering if you have in your code one mask that says ones and zeros, so you can just replace the ones in the positions with the ones and zeros or something like that, or
Well,
you have to.
what I
Yeah.
do is that I take exactly the same no data value stored in the raster. So all these calculation is depending on what you did with your with your flow accumulation and flow direction. So
Okay.
so it's going to align all the rasters of temperature and evapotranspiration and rainfall to match it. So here, when you download your rainfall, there is values everywhere. And when you mask it with your DEM inside Hapi, it's going to store the no data value in order to, when you plot it, it doesn't appear. So it's going to take this no data value and it's going to put it in all your meteorological rasters.
Okay. Okay. Good. So you have, and you can go through time step by step, and that's will be the way to see the whole thing. Yep. And also you can aggregate or make analysis of all this surface runoff, right?
Mm-hmm.
Good.
And here, after you calculate all this metrics of all errors, after here you whatever how many gauges you have. So Bison and Bison it start with 0. So this is the gauge that I was saying it is at the upstream, and it has a very big difference in the catchment area. So it is supposed to get discharge from 124 square kilometer, and it is actually getting discharge from half this area. So you can see here. And another thing here is that there is a problem of this is the simulated one and this is the gauge. So based on the rainfall data, the peak is coming a bit early than how it should be. So this is a problem not as a model structure but as a data. So yeah, and another gauge. Here is another gauge, and you can change this gauge I by your
Just maybe
number.
for sake of clarifying, meaning that what you have right now is the run without any calibration,
Yes,
number one, and number two, after the calibration is done, the assumption is that it will place the coefficients and the parameters of the structure of the model such that it will drain the area that it was estimated there 64 and not the area that was complete, which
Yeah.
will be like trying to match a bit the new distribution of cells. Now that's fine, that we will do. However, in this case that you are showing the big difference in the areas, wouldn't be more logic to try to correct the problem of the difference in area via making some sort of procedure to include cells that seem to be have moved to another subbasin? Because in principle, if with a high resolution you know that this is the area, and when you bring it with low resolution some have moved into another, will be better to correct it before you start to run this. So in ArcGIS there, try to make an assumption that will correct that difference in area, which is quite big.
Exactly. So this thing is it has to be pre-processing from GIS, because yeah, whatever you enter as a DM, everything will be depending on that. So yeah, as I showed here yesterday. So for example, yeah, here this cell. So there is a big part outside. So that's the case that we have seen in this in this first gauge. So it's half the flow is coming.
Yeah.
And it's actually debatable, like whether we should compensate this with calibration or not. So yeah, and yeah, here in this, so as I showed before, we have a lot of inputs inside inside this Quello. Dot, if you write underscore dictionary underscore, I guess that's going to plot up list attributes. Yeah, so there is a method inside the object, the catchment object, called list attributes, and this list attributes is going to give it's a dictionary, and this dictionary we can make it like this. It gives us the keys. Also the keys it's going, yeah, so you see this value. This is the value that is stored. That's very big. So yes, clear output. So this is the value that's stored in these cells. And if you tried before and opened any DEM, so it has an attribute. It's called no data value, and this no data value, where it is not showed. Okay, so it stored some number. And what I decided when I was doing the calculation is that, okay, I'm not going to store anything that I decide. So I will take the number that is decided or that's you stored in your DM, and I'm going to plot it here as well. In order, if you want to plot it, GDAL is understand that this value is not a value of evapotranspiration, but this is a no data value that's stored in the raster. So it's not going to show it. Okay.
Yeah, because the value, in fact, if you see there is plus 38, so it's quite huge number, no?
Yeah, so if I open now GIS, Arc or QGIS, you will find like similar numbers. I just take it as it is, it's stored in the flow accumulation raster, and put it here.
Okay.
So, yeah, so using this method, list attribute, it's going to tell you everything inside Coil, inside the object. So it's quite big. A lot of stuff. So this flow direction table is what's telling Hapi which cell it has to be run and at which order. And here is a flow direction raster. So as you see, it is yeah, I generated this flow direction using ArcGIS. So if you this 255, this is the no data value here, and if you look at this shape, that's the shape of Quello. So down in the figure, you will find that, yeah, that's the shape. So it has how many? It has 8 direction, and that's what the what is this flow direction algorithm is doing. So every cell has 8 direction to go, and those 8 direction having index 1, 2, 4, 32, 64, 128. If you generated your flow direction with QGIS, it's going to give you other numbers than this 1 and 2. And that's the flow gauge. Yeah, so these are all the data that's stored inside.
And what about the calibration process? Did you already talk about it?
No, not yet. So I have it here. I'm going to show it after.
Okay.
Okay, and here this animation method inside the object. So every this option argument, this option parameter, it has value from 0, I guess, to 9, and for each one, it is going to show different value, different output. So it's going to, I put 20 day only because this is rendering some stuff inside Matplotlib, and because we're using Jupyter, so it's taking this and converted to HTML, so it's taken some time. So yeah, here it is. So the first option is the total discharge, and it is simulating like this. And if you don't like this number that's plotted in the top, so there is here argument. Yeah, plot number, you can put this plot number to false, and it's not going to plot the number. And yeah, if I do this false.
And one question here, it's this what you are showing here in the are individual values of surface flow. So in fact, it's not the flow accumulation. Is the so I see here values in each one of the cells, or it is the flow accumulation, because I see the values are quite low and some of them might not. Yeah, for me, it's not
Not what?
clear why. Yeah, two values are bigger than the one in the middle, and then it seems like if it was drying the river in the center instead of growing, but maybe I'm
no,
mistaken.
this center here in the color bar is bigger, so flow is going into this big branch. Yeah, here that's the river, and it goes here and goes up. So here are the bigger values.
Yeah, so all the ones that you have here in the lower left side of your screen, it seems that they are not routing anything.
Those are the divide. So value is very, very small. So if I extracted the hydrograph in any of those cells, you will find at this time step they don't have they have a very small value of discharge.
Do you have a function to show those hydrographs or those time series?
Not yet, but it's an array. So whatever indices. So if I put maybe.
Yeah, you have to put the second dimension, the time, leave it, and put the dimension of x, y fixed. Probably that will help you, right? But okay, I think that don't just continue. Now I got your point here. I don't know if anyone has questions, if it's running well for everyone.
Yeah, well, let me see. So it is 13. So I put 12 and 1 and everything.
I have a question. Is only maybe why you decide to do it in these 2 years?
Mustafa, Gonzalo, yes, go ahead. I didn't get the question well.
Okay, yes, is the script is from 2009, from the plot start, and the at the beginning is like 2 years of information is from 2009 from 2011. The question is like why you decide to do it for these 2 years, or it's only for the information, or?
Well, that's a duration of calibration. So whatever you like. So I have I guess I have 4 years, and I decided to take 2 years and 2 years for calibration. But yeah, that's totally depending on what you see. I'm trying to import Matplotlib dot by plot as DLT. Okay. So here why it is not. Yeah. So this cell is this here. So as you see, the biggest value is 2.5. Okay. So yeah, and so yeah, those cells has very small discharge. So this is this cell that I plotted here, and outlet. So maybe I plot. Well, the outlet is we can plot the discharge at the outlet here from gauge, because gauge number 5 is at the outlet. Yeah, yeah. As you see here, it's an array, number array. So you can, whatever indices you bought here, it's going to give you the discharge of any of these cells.
Okay, good. Yeah, sorry to rush into the part. So what is missing? The animation is already there, and store results into rasters means to save it as the rasters. Okay. And the next thing is that you're going to show is the calibration, right?
Yes.
Maybe we could move into the calibration, because I think the other part, I don't know if for me it's very straightforward, but I don't know if the others, does anyone think wants to see the last part of the or do you want to follow these last two parts?
It is just you press here in order to save this plot. So it return an animation object, and this animation object here, you just save plot, and you bought the extension MOV or MB4 or whatever, and you press enter, and it's going to save it in this path. The thing that you have to do is that you have to. Oops,
you put it with us. You save it as GIF.
No, I cut the description, but
yeah.
Well, it's
I
a,
know. We can see you.
it has to be here. So it's a codec in order to be able to save any videos. So yeah, so it is that symbol. So it doesn't have here. Yeah, so this website, just it has, if you are using you download it from here, or you check what is this is a codec. You check what Linux you are using, Linux or whatever you are using, and this is going to save. It saves the rasters. So you just put here. It has the same option index. 1 is total discharge, 2 is the surface discharge, only 3 is the lower zone or base flow, and you press. You just put the period you want to save it, and give you a sign it's saved. And if I opened this where the bus, this one, that's the bus. Okay, where it has already saved the files, and studies. So here, so these are rasters here, as you see. So you cannot open it like this from Microsoft Photo Viewer, but you put it in you can just drag it and drop it in QGIS or ArcGIS, and here is the animation. So I save it. I saved a very short time, and you can actually control how fast it is with this. Where it is, there is an argument to specify how fast the simulation should be.
Frame per second. Yeah.
Okay, so now the calibration. So it is exactly the same procedure. So as I said last here, this object catchment it is a super class, and all the other classes inside Hapi are subclasses from this class. So all these methods that I showed here, this is this calibration object is another object, but it is a subclass from the catchment object. So it has exactly the same methods and same attributes, and it has one only extra method, which is a calibration method and the calibration algorithm. But you have exactly the same procedures here to read the data. But extra thing is that how do you want your catchment characteristics, and how do you want these parameters distributed over your catchment? And that's what I'm going to show now. So reading exactly the same inputs as it is, like what we did in the running. So read the data, and now here is we start talking about the calibration. So each one of those parameters in the calibration has a value, and in the calibration we decide we write the range that we want it to be. So for example, you have to put this lower bound and this upper bound. Yeah, it is. So
you have 12.
Yeah, so here we have 10 because we don't have snow considered in this case study, and we have 2 parameters for Muskingum. Okay, and yeah, so this rainfall correction factor is a value that's going to multiply it by the rainfall in order to take care if this satellite data, this MSWEB is not correct enough, or yeah, whatever.
Yeah, no, in fact, that one is more related to a correction factor due to the elevation zones, and it is expected that depending on the where you are, you will have a so yeah, I don't know what was the criteria here to put 0.7 and 1.3. However, yeah, you could leave it as it's always is normally is less than the amount of rain that you have, so it should be 0.7 or something. If it's a rainy place, well, you can go to 1 point something. So the yeah, that range. I don't know what is between that one, but okay, it's.
Yeah, so these values you fill it depending on your knowledge of the catchment. So yeah, you have to read some literature about how these values should be, or yeah, from people who knows about the catchment. Okay, and yeah, Muskingum values. So Muskingum, the value x. Yes. K is a value.
Maybe another thing. This Mustafa, maybe here just good to mention that you use the parameterization from this paper to have some parameters that are already in certain range, so certain
exactly. So
let's say values. So,
yeah, so these boundaries I extracted from this global parameter that I replicated from this paper. So yeah, and I have a sensitivity analysis in the algorithm. So after you run your calibration and you found that yeah, it runs for a couple of days and it didn't get the performance criteria that you are looking for, you can run the sensitivity analysis to check which parameter of those is the one that is improving or changing the performance with a big degree, and you redefine those. So probably this range of this factor that is multiplied by evapotranspiration, yeah, we want to increase this 0.3. So there is other steps. Yeah, you can redefine those values. Okay, so the calibration algorithms that I'm using, or like most of the calibration algorithms, so they have two ways to define the boundaries for the values, or if you have a condition. And one of those boundaries are one of two types: equality, where you say you have equation to define your the values that should not be, or you have, for example, x equal x plus y, or x plus number equal another number. So this equation called equality constraint. Okay, another type of constraint called non-equality constraint, where you have equation greater than or smaller than a certain value. And because of this non-equality constraint, you will have a lot of runs during the calibration. And actually, the calibration algorithm try to assume some a set of variable, a set of numbers for this parameter, and after it calculates, it calculates whether this constraint that you put is met or not, and it can run a lot of time, and it doesn't attain the condition that you put for constraint. So here, in this K and X, they have unfortunately non-equality constraint. So some way, we don't have to go very in detail here. I convert it into equality constraint, so it is not non-linear, it is linear right now. So the K of Muskingum, it's a time variable. So it tells Muskingum how much is the lag time in the hydrograph. So the unit of K is the same unit of your model. So it's a daily. So here it should be daily. So it should be half a day, 1 day, 1.5 day. So here I'm putting 100. So this 100 is not days, but it is just, it's going to choose a number. I'm generating numbers between for example, I'm 5, 1 day and 5 day. I'm generating 100 number. Okay. And the algorithm is going to assume one number between 1 and 5, and it's going to assume 100, and it's going to pick 1. Okay, you don't need to go in details too much detail in this. If you are using another calibration algorithm, probably you have to define K between 1 and 5 or 1 and 2, depending on how much you see your hydrograph should be lagged. And this X value is between 0 and 0.5. Okay. And yeah, here, so you have to, this text file, you have to read it here, and you have to put it, you have to read it through a method called read parameter bounds, and you have to say, are you going to consider snow or not? So this snow variable is here, it's defined 0, so I'm not going to consider snow here. And that's why we have only 10 parameters. So we have another 5 parameters for snow. We are not putting any of them here. So we read this, and now with the way that we want to distribute the parameter over the catchment, do we need to have one value of parameters in the whole catchment? And that's what we call lumped parameter. What we need here, I can show it. So for example, option number 8. What's number 8? I guess it is. So this is. So 8 is state variable, so it is a water content, and those are not. Okay, so this is the water content. If I put 5, it's soil moisture.
What is the water content that you are adding there?
That's a state variable. One of the state variables.
But it would mean it's like a soil moisture, no?
Here
You
the-
have soil.
here
Why
is
is different soil moisture and water content?
That's another state variable. I don't remember exactly.
In HPV is not like that as far as I remember.
So soil subroutine, and soil moisture, and
There is a water content which is associated to the snow.
it is the water content, I guess.
It's called,
So
yeah, that's a snow water content. But that's if you don't have snow, that should be 0, if I'm not mistaken. You say water content, I see there, yeah, old and new. But water content is the water content in the snow. It's like the snow routine.
it is this.
But check out what is.
So it is water content, and it is coming from the snow subroutine, yes. But this one, let me check.
Yeah, I know. So what if in this case you have a snow 0, so that should have given 0. Okay. Okay, so that's important. Yeah.
So here, what I was talking about, how do you want to distribute your parameter? So if you look at here at the soil moisture, you see here it looks like all of those cells has the same value. All of these cells in the middle has the same value here, similar value. So that's what that's the closest way to reality. So it's not different value of parameter for each cell. These parameter, when you use different for each cell, you will find it here crazy. Everyone has a different value. But yeah, so this object, so this is a new object. It's called distribute parameter, dist parameters, and this object, it has a lot of methods inside into how do you want to distribute your parameter. So if you give it here, you have to say how many number of variables do you have, and if you want to make one of those variable lumped in the whole catchment, so it is the same value in the whole catchment, you have to say this number variable and and the position of this number. So for example, here I said 7, so this 7, that's the position of the number. 7 is this one because Python starts from 0, so it's 8 here, and this one is the precision parameter of the base flow. So what I decided here is that I want the base flow to be lumped in the whole catchment. It doesn't have any variability in the catchment. If you decide that you want to make,
okay, that sounds good. But maybe a good example for everyone is that normally you would expect more homogeneity in the groundwater systems than in the surface. So you would like to have variable the surface parameter, and in the groundwater systems, which probably is the lower tank, you would like to have them different.
Yeah, that's the lower tank. That's the precision parameter of the base flow. So that's what I put it here lumped.
Okay.
And the others are changing. So yeah, that's considered here. If you want to put any other parameter, you want them to be lumped. So you have to put here 3. So this parameter will be lumped in the whole catchment. It doesn't change. If you put this one, if you put 10, so the percolation will, if you put 11, Python start with 0. If you put 11, this one is going to be, if you put 9, this one is going to be lumped in the whole catchment. Okay. So yeah, so in this object, I'm instantiating here. Instantiating here the object with all of these. So you have to give it the raster of the flow accumulation in order to take these values and in order to distribute it over 2 dimensions, and number of parameter, which is when we have 12, 10 for HPV and 2x k and x of Muskingum. Number of lumped parameter, what we decided here, it is 1. The position of this parameter, and function is 2. What is this function? So I will open this parameter. So how many options we have? We have here 4 options. Okay. Do you see the functions?
Yes.
Okay, so first option is lumped. So you have to give it 10 parameter and it's going to make it equal in the whole catchment. Let me open it. So I want to open the array and show it to you. Yeah, here it is. So it's called spatial variable function. So where is that your variable function? Oops. Yeah, spider, sometimes it opens the object and sometimes this thing is running like this, so it's not going to show anything. So maybe I close it and I open it again. And in the meantime, yeah, I continue here. So you pass all of these variables here, and you created another object here, and this object you're going to pass it to the calibration object. So right now we have the main object, which is the calibration, and we have another object. It's a spatial variability object that's going deciding how to distribute the variables over the catchment. The gauges exactly the
Sorry,
same.
I have a question.
Mhm.
If you, in this case, you have only one lump parameter, but if you have more than one, you do a list there, like in the place that said lump par post, like you do a list, or you have to assign it differently.
What do you mean?
In the same part that you were before, I don't know.
Mhm.
No, like, well, you were explaining, for example, that you have that is the lowest tank. But what if you want to have also the other tanks lump? Well, the first tank, for example, like more than one parameter lump.
Yeah, so you have to write here, I have 2 parameter, and here you have to tell it which
list.
position, so 7 and 8. So it's going to take the 7th and 8th place, and it's going to make them all the same value in the whole catchment.
Okay, maybe I have a question there also associated to that. What if I want 3 different or 4 different parameters for dividing your region in 4?
Yeah, you put here 4, and here you put 4 location.
Okay, but if I wanted this for my point is that you have
no.
your region. Yeah,
This regions
you got
have
my point, right?
Yes, so you want to have 4 sets of parameters, right? Every region has
yes.
the same set of parameters. That's another thing in I called it here HRU.
But
so
maybe not too complicated. If it's possible, just mention that it is, because I don't want to distract, because I know that it might be complicated. But the key message is that if it's possible, yeah.
Yes, it is possible, but
like
you have
sending a mask where I want. Yeah.
Exactly. So you have to provide another information, and instead of providing this flow accumulation raster, you have to provide the raster that you have classes, land use raster or soil type raster. So this additional raster, it has 4 regions, as you said. So this object is going to generate 4 sets of rasters. So we have 10, we have 12, so it's going to generate 48 variable, 48 parameter. Okay.
Yep. That's good. Yeah.
And here I wanted to show, I hope.
Sorry, I have another question.
Yes.
What does it mean? Like, I don't know. Like, can you put the other, like it says KLB and KUB, I don't know, in the other.
The name of the variable, you mean?
Uh-huh. But in the other one, you put like 0.5 and I don't know the other number. You can see it. Yeah, the KLB that is 0.5 and KUP that is 1. What does it mean?
These are parameters in the HPV.
In
So
that?
what does it mean?
No, but not there in the other part.
Which
KLB and KUB.
yeah,
After the number of parameters that it's called.
This is the upper value
You
and this is
assign
the lower
KLB
value.
and KUB.
Here, yes. So this is okay. So you remember when I talked about this non-equality constraint that I don't want it to be non-equality in the calibration algorithm. So I created some way to linearize it to make it between 0.5 day and 1 day. So this is the traveling time, the travel time that Mustang is going to take to make. So it's going to decide how much is the lag in the hydrograph when it travels from one cell to another, and it's going to search for this number between 0.5 and 1. So what my calibration algorithm is doing, so it is taking 0.5 and taking 1, and it's searching for a random value between those 100 random values between those two values. Okay, so in your catchment, if you decide that you are going to have cell size 10 kilometers, 10 by 10 kilometers, so probably 10 by 10 kilometers, that the water, in order to travel from the center of this cell to the center of another, the cell that's downstream, so it's going to take 10 kilometers. So probably you can increase these values, make it between 0.5 day till 3 days. Okay.
Yeah, maybe I'm confused, Mustafa. So why is this here and not in the file that you read with the upper and lower bound? Why you have to express it here? This is the same, right? Is you have k equal k position 1 and the other one k position 100. So why you have to put it inside the code if you have it already in this file?
This is well, this is considered for all of them. That's going to be like this. And this in case you decided to make it as a distributed, every cell has different values, so you can change this. So it's a way that I did it in order to prevent this non-equality, which makes the calibration a bit longer.
Okay, so it's only for the sake of using your lumped distribution. If you do not use the lumped or trying to group parameters, you can use this one and it will use this one. You don't need to define it there.
No, actually you have to define it here. So it is input.
Even, and so why you put it in the parameters there?
Well, that's yeah, it has a, yeah, if you it's about this non-equality constraint for the calibration algorithm. So if you are using another calibration algorithm, so you don't have to put this position, you don't have to linearize what I said to prevent this non-equality constraint, and you have to put here 0.5 and 1.
Mm-hmm. Yeah,
but,
okay, yeah.
Yeah, so, but if you are using the calibration algorithms that I'm using, so you have to put here a position. So as I said, it's going to take these boundaries 0.5 and 1 and generate random values, 100 random values between them, and select randomly a value and try it.
Okay, yeah.
Okay, thank you.
It's not opening here, but what can I do? So, well, so it has, so when you generate the variables here, so it's going to store it in a parameter called parameters, and this parameter with a capital B. So if I did like that and take this variable and parameters and run it, so it's not it did not create it yet, but it's going to create it inside when the calibration runs. It's going to generate. So right now we created the mold, we created the blueprint that is going to be used inside the calibration. Okay, so here we run these cages exactly the same, and we come here to to the objective function. So what you have to do is that you have to write whatever objective function you want it to be, and you have to pass it to this method objective function. So you have objective function and you have some argument or some parameter, you pass it to your objective function. So write whatever you want and pass it to the algorithm. So what I did here is that when I showed before this table in the gauges, and I put weights. So dot gauges table. So at the beginning, I decided, okay, so I want to give some gauges some gauges are more important than the others. So I give this gauge a very low weight based on the area, how much area upstream of this gauge corresponding to the total area. And yeah, so if you sum all of these weights, you will have a value of 1. So the gauge that's at the outlet has more weight than the others. And yeah, so whatever argument you are passing here, you need to calculate whatever you want inside your objective function, pass it here, and put it as a list, and it is going to be passed. The algorithm is going to pass it to you back here inside your objective function. And I was calculating root mean square error as an error, and summation of all the errors of gauges multiplied by the weight, and that's the total error that the calibration algorithm is going to try to reduce. Okay, and here the calibration algorithm that I have here is called harmony search. So it has a lot of other parameters that you can decide in order to make the algorithm reach faster or take shorter time to reach the minimum value. I guess I should not go in detail inside it, but yeah, so
no need. In fact, it's just
yeah, it's too complicated, but yeah, you can read about it
but the
later.
important is that we know that these are the parameters you need to define right now. But maybe good to know this. No need to go in detail into the algorithm, but this what will do these parameters in terms of sensitivity of making it run more or less time and be more accurate or less accurate. That's maybe good to know. So you have HMS Harmony Search 100. Yeah.
Yeah. So harmony memory size. So harmony memory algorithm, what is going to do is that you decide here to have 100 set of parameter, and those 100 set of parameter is what, if you used genetic algorithm before, that's the population size. So it has 100, and it is going to have 100 set of variables the whole time. And every time is going to take, for example, the best 20 of those 100, and it's going to generate another 80 set of parameter from those 20. So all the time has 100 set of parameter, and it's changing those 100 based on the best sets of parameter in this 100. So that's called the harmony memory size. Harmony memory consideration rate, it's another parameter. I don't recall right now what it is, but actually what it does, these are like probability. So it generates a random number between 0 and 1. And if this random number is bigger than this number, so it decides to change this variable or not. So we have 12 parameter. It generates random number lower than this number. So it doesn't change the value of the parameter. If the generated number is bigger than 0.95, it changes this number. So this variable, it makes the algorithm decide to change and go crazy in the search space of this parameter, or it focus more in the parameter that is generating more error. And this batch rate, I guess, harmony memory consideration rate, and this is it's called batch rate. It's another random number it's going to generate to decide to change or not. So, and this is bandwidth. Bandwidth is 2000. So what is going to do is that it's going to take the upper and lower boundary of each parameter and is going to generate 2000 number between those two limits, the upper and lower, and is going to select random variable in these 2000 random numbers. Here, file out if you want to store the history of the calibration, all of the trials that's going to do. This one is going to do that, and yeah, here you give it the path and name of the file that is going to store it, and you run this. I already run this. Okay, and here run calibration. So now the object has a method called run calibration. You give it the spatial variability function, and you give it this optimization arguments, and print error 0, or I guess it's going to print the value of the error for each time step. So it printed this. So now it's going to, yeah, so here you see we have 5 gauges. 1, 2, 3, 4, 5. We have 6 gauges. That's the error for the first gauge, error in second gauge, error at the outlet. So now you have to run it and leave it for a couple of days.
Depending on the processor that you have, right?
Yeah, that's yeah. Never run calibration in your computer. Run it in a server or something. So
yeah, and another question: to run this in parallel, is taking in this moment parallel processing? No, it's just running with the cores that you have.
well, as you see, where so it actually had a parallel here. So this argument I pass it none, so don't use any parallelization. But I had some problems with the MBI installation, so I am actually considering to do that, but not using MBI, but using CUDA or this multi-threads that there are some libraries.
Okay, so the implementation is there, so you need to have installed MPI, or you need to have something.
I don't guarantee that it's going to work smoothly.
Okay, yeah.
But it is there, so
it is there, so you have to test it. Yeah. Okay.
Maybe we can test it now. I don't know.
Yeah.
Yeah, but it's still running. It is still running, so I have to stop it, restart kernel. I have to run it all again. Yes. Here. It didn't run here. Yes. What happened? Yeah. Oh shit. This running. What did I write here?
Morphilo. Go down. Let's see the error. You
but only
have to enter a
parameter, yeah, so
only one, because you change, you put 4 parameters and put only one, put one there.
So yeah, you see, I will show you. I actually put a lot of validation stuff here. So here, if you have number of parameter bigger than 0, so it is going to calculate how much. If you don't see this, so it's going to calculate how much the number of parameters that you have to put in the in those two files. So it is going to guide you how much should be here, okay? Because actually, if you decided like what Gerald was saying, you want 4 sets of parameters, so you have to copy those and you have to paste it here 4 times. So 1, 2, 3, 4. Okay, so it's like this. So it's going to guide you. So whatever value you put is going to tell you, no, that's not correct. You should put this certain number. So there are a lot of similar validation inside the code. So yeah, and these assertion errors is what tells you what's wrong. Right here, objective function, and this is parallel, and let's hope it's going to, yep. Let's check my processor.
Yep.
It's using all of them right now, right?
Yes, it seems so. It's all homogeneous, and you have 8 cores. Nice machine.
It's a working machine.
Yeah, it's a lot of. But yeah, maybe the point is that if we run this in Surf SATA, it will
run faster.
It will be able to take.
But printing the error, I don't know why it doesn't show. So I should actually see the running this printing of error. It should be like I have 8 cores, so it should print 8 at the same time. But that's I guess when printing.
Yeah, the printing is different. It's only printing the result of one. Yeah, you're right. Yeah.
So, but yeah, when you print something and your kernel actually show when you write flush, so it has the value and it is already calculated, but it doesn't show it until it finished calculation or something like that. So yeah, the parallelization, I don't guarantee to work perfectly right now. I'm working on it, but yeah, it is there. And yes, so after it finish, you have here yeah, so it's going to generate a list. So the code is working with one-dimensional array of these parameters. So it has a vector of parameter values, and the distributed spatial variability function is going to take this one vector variable and it's going to distribute it again over your domain. So what the calibration algorithm is going to do is that it's going to generate a list, a vector of variable. You give it back here to the function to distribute it over the surface, and it's going to create a raster for you for each parameter, and you are going to save it here using this method. So here,
okay, and how to see the result of the
calibration?
In the graphical representation of the time series of the outlet, because I imagine there's 5 gauges, you can also visualize them again, but I don't see the object that you had, or you look coello dot.
What do you mean? I didn't get it.
You finish your optimization there in the calibration, not here in the calibration here. You just finish. I want to see the the results of the model on the discharge, on the 5 values that we were calibrating, or 4 values, so 6 values that you have there.
You save.
How can I see measured versus? No,
yeah.
But yeah. So
you save the parameter and come here to this code and run it again.
You don't have anything.
You can just copy this.
Okay, and
not
say.
copy. So wait. So you just have to where read parameter, save the parameter, read the parameter using this object, and use the same object as of this calibration. It is a subclass from this catchment, and run it again. So yeah, so this piece.
Okay, and if you have this is saving all the results, so we can see all the parameters that were. So to build a Pareto front, you will need like
to
identify what were the last.
This is a single objective optimization, so there is no Pareto. I'm also
But then, so you are Yeah,
Mhm.
you are linking all the results into one. In fact, it's a multiple objective, but you have placed it in one function, right?
Yes, exactly. I sum all the errors multiplied by the weight, and I make it only one error.
So if I want to see the history of how the parameters were running in the four, in each one of the dimension or each one of the gauges, is not possible because it's have been all
No.
aggregated and you were only storing the
Yes,
result. Yes.
I'm only storing one
Okay.
one value of error. So here,
Okay.
result.
Something to do for me is looking at the multi-objective one.
Yeah. So text. So that's what you are going to see. So
Yeah, I don't know if
so 1 power 1 punch. So no, this is not good to show.
Yeah, still it will take you a lot of time starting with a bad result.
So here 125. So that's the summation of all errors. So this is not good as well. So this is empty. Empty as well. So empty as well. So yeah, no good result to show. So
Okay, but then in your
30,
experience,
yeah, no,
how-
here is 30. So 30 is the summation of all errors. So if you are looking here, so yeah, so 30 it is 77 here only at the last gauge, and all the gauges. So here after sometimes after 50 after 85 runs it reaches 30 for all gauges, and yeah. So yeah, so I was run it only for a couple of days and I didn't tune any of the parameters. So I just, yeah, it's working, leave it as it is. And I was more working on how to distribute the parameters and not to have crazy everywhere, or how to generate regionalized parameters. But yeah, in principles, everything's working, and it depends on how do you want to calibrate your model. If you don't like the calibration algorithm inside here, so you just have to use the same calibration objects that I have here, read everything, and use this distributed spatial variability in order to pass the parameter inside it and distribute it into a surface. And yeah, there is another calibration algorithm called deep, and you can use that, and it's going to give you a good result. So you don't need to run this harmony search. You can use whatever calibration algorithm you want. Yeah, so
okay.
that's the calibration.
Good. Yeah, I
I
think
have
it
a
was.
question.
Go ahead, Angie.
Sorry. So as I understood, like all the obtained parameters in the calibration are the same for each sub-basin, or well, because you said like you divide it in like in the I don't know, the cells have the same parameters.
Yeah, Lambda parameters. Yeah, what do you want to do? You want to distribute it differently, or how do you want to do it?
Yeah, like I mean, like in this case, these parameters are the same for each sub-basin. Is in that case, I'm not like
Has the same parameter for each
yeah,
cell.
because like you were saying, like in this case, they have
Yeah, we don't have here sub-basins.
all
We
the
have
same
cell.
parameters, but
Yeah, so
yeah, well, cell, sorry.
yeah. Say what you want.
So in this case, like all the cells have the same values.
Yeah. It will, yes.
Okay. Okay,
Yes,
but
but maybe yeah, I get the point. So if right now we have only one option that one of the parameters is lumped in all the basin and the other parameter is different in all the basin. Is that the case, Mustafa, or not?
What we use, I don't remember the function we used here.
Just in general, yeah. It will never be different because you cannot have distributed region. So you have that lumped and the other ones will be different. Yes?
So
Or not?
we used function number 2, and function number 2 is, no, actually what I did is that I different everywhere. So yeah, here as you see, I have four algorithms, and the first one is you give it 12 parameter, and it is going to make those 12 parameter the same in all cells. The second one, you give it parameter, and it's going to consider different parameter in each different cell, and that's what we choose there. And actually, that's why it is printing. Yeah, so you see here, those are the number of variables that the calibration is trying to find. Here, where it is 900 or something. Yeah, you see here, because 12 multiplied by, yeah, here, there is an object actually to see how many numbers should the algorithm is going to search for. And it is here. So this attribute, so it is trying to find 980 parameter to reduce your error. So this is garbage. So don't use that.
But maybe the question is what I understand, that maybe thank you, Angie, because it also raised the question for me. If this is one parameter, they say lumped per position, you say then function equal 2. So if you put function equal 1, right now you put function equal 2 and you send him a number of lumped parameter equal 1. So what is happening there? What is the sense? I was getting from what you were saying is that these two values no lumped parameter equal 1 will mean that one parameter is going to be lumped in the whole basin, right?
Yes.
And the parameter is the parameter position, that is this number 7.
Exactly.
Yes?
Yeah, that's true.
So a parameter position means which parameter it is. Okay. Okay. Then if you go into your DP, what I see there, DP, in that one, you have a function equal to. Can you not change it? Sorry, it makes me keep it there. Don't move the mouse, please. Yeah, you have here function equal to. Yes, function equal to. And as you just mentioned 1 second ago, function equal to means all the parameters are different. But now I am wondering, first you mentioned that on the left or on the first 2 lines, and now you are mentioning that it changed. Can you explain what is happening and what happened if I have function equal 1?
You have function equal 1, so in the you have to provide those two. It depends on you have to provide those upper bound and lower bound has only 12 set of parameter, and it's going to put them everywhere. Okay, so this function number 2 is very, very general. So if you put here number of lumped parameters 12, and you put the position, all the position from 0 to 11, it's going to be lumped everywhere. So function number 2 is the very general one. And of course, it's to distribute these values over the whole domain. It's taken more time. I created another more simple function, which is the function number 1. You have to give it only 12 values, and it's going to assign them in all in the whole array. So I actually
don't move it. Don't.
I want to run it, and I want to show you how this DB. Yeah, so this spider thing, you actually can open the object, but it works 1 time and 100 times doesn't work. So I'm going to debug it and to show you how it actually generates the variable in the numbers inside. So
Yeah, due to the large amount of parameters that you have, it's no need to do that, Mustafa. You will not be able to show me too many things. You will show me a bunch of values there in an array, which have not too much to show me. But maybe you can explain without going into the. Don't worry about the error right now.
No,
Can
this
you
error
show
is
again?
it is not an error. So to open any object in Spider, it has to be pickable, and somehow it's not.
Yeah,
It's
not
considered.
pickable, yeah.
So here, so function number 2, I said it is the 3D function. So it's generate everything random, everything different. Every cell has different values. So you and so from this very general function, you can actually make everything lumped. So you have to give, you have 12 parameters. So you have to give it number of lumped parameter 12, and you have to give all the position. So it's going to give you the same result as if you choose function number 1. Okay. If you are using this one I created for the lake case study.
Yeah, but maybe what it is.
What?
Yeah, difference or well, for me, I don't know if for Angie is the same, but for me, if you go to the other one, go to the so keep it in the Jupyter notebook, because the problem is in the Jupyter notebook, or the problem, or the probably the gap on what I'm trying to make sense out of what is there. So you have two variables here, that one is called no lumped parameter and lumped parameter position. Those two are defining one thing that will make one parameter all over the basin. Clear? Yes. Now you have a spatial variable function dp, which will distribute parameters around the whole basin.
Yes.
So I would expect, and this is just, I'm guessing, I'm just expecting that if you put these two parameters, no lumped parameter and lumped parameter position, will mean that you will put all the parameters variable, and only the parameter that you are mentioning is lumped. That I would expect that. Doesn't matter whatever you are saying with all the other functions, I would expect that. If not, why you ask me to put these two? Now maybe maybe it relates to another thing, but I don't know. So can you explain a bit without moving the slide, only with your own words?
So
what is doing this DP?
This DP is going to distribute your number of parameters over the domain, over the cells.
Good. Yeah.
Okay.
And how? Yeah.
This number of variable equal 12 is how many parameters you are considering in your lumped model. Okay. If you consider the one with the snow, so we have to put here 17, 15 for the HPV, and 2 for the Muskingum. If you are using the one without snow, you have to write here 12, 10 for HPV, and 2 for Muskingum. So far, so good.
Good. Yep.
Here you have to decide which of those 12 parameters is going to be lumped. Okay, you wrote one parameter is lumped. So which parameter is this lumped parameter? The one is in position number 7, and that's it.
Yep.
If you don't want to choose those two parameters and you want to choose all parameters are lumped, you have two options. Okay, the option number 1, which I made it as a special case, you just have to choose in here in this function. You have to choose function number 1, and that's it. You don't have to do anything else.
So he will make no use of these two parameters above. Everything will be the same.
Exactly. So it is just one for loop that this DB object is going to avoid. So, which is
okay. And now the other case.
And the other case is that you choose the same function number 2, and you put here how many number of parameters you want it to be lumped, all the parameters. How many of those parameters? 12. And you have to put here from 0 to 11, which is those 12 position. And it is going to match these numbers with with the
Yeah, that input, that's a boundary to start.
Yeah,
Yeah, I know.
yes.
Don't need to show it. Yeah, these are the 12 that you need to have. If you put 2, then you need 24. If you need 30, you need 36,
Exactly.
and so on. Yeah,
Exactly.
but that's not the point. Maybe the point is more physically into the concept of the catchment. So if you put number 2, it will fix lumped the number of lump parameters that you put and the position or the definition which parameter did you select there in that list, and those ones are going to be lumped. It doesn't matter if you put 2 or, well, it is important that it's 2, so all the others will change. Only the ones that you selected as lumper will be fixed.
Yes, that's what it's going to do.
Okay, good, then it's clear. Yeah, I don't know, Angie, if you got it.
No, that was a question. Thank you.
Yeah, also for me was the question. Good.
Okay, so yeah, other questions?
Yes. Yeah, I have a question, not related to the calibration we're doing right now. Yeah, thank you very much for the session. It was very informative, and yeah, your work is really amazing. In your documentation, and also yesterday, I believe we also discussed about how to like interpolate the data from gauge data. Like for example, if I don't use the satellite rainfall product, but I use the data from the gauge, then how can I, like in your package, how can we interpolate that data? Yeah.
So I have a package here called a statistical tool. And inside this statistical tool, you'll find 2 methods that I created, which is this inverse distance weighting. So it's going to relate to calculate the value of each cell from all gauges based on inversely with the distance from each gauge. And another method here called inverse square distance weighting method. So it's going to relate each gauge to the cell inversely with the square distance. So those are 2 methods I created to interpolate values. So you just have to, yeah, here are all the descriptions is written here what you should do. So for this method, you have to read your raster, your DM into GDAL, and you have to get the coordinate of the gauges, and the coordinates, of course, has to, yeah, here it is, yeah, it's written, you have to read them in the dictionary, and it has 2 keys inside the dictionary, X and Y, and of course, coordinates has to be the same coordinate system like in the DM. And what else? Yeah, so yeah, it has some parameter here, so you have to provide it, and yeah, you will have at the end a 3D array with all raster for each time step.
Yeah, maybe to help on that. So this makes the interpolation with 1, right?
Makes the interpolation with what?
So you mentioned that it works with 3D. So the third dimension is the time, right?
Exactly, yes.
So the raster that you are importing here, I use the library GDAL, import raster read whatever from the, as you showed before, and then I have everything in one variable, and that variable is the first argument to this function, right?
This raster,
and that raster should be, yes, that raster should be read from GDAL.
Exactly, yes. So here,
and that should have 3 dimensions. If you
no, the raster has to be the DM or flow accumulation. So it's going to generate 3D. It's going to generate rasters exactly the same shape like your DM.
And what about the gauges? So the gauges, when do you read the gauges?
Yes, you have to read the gauges here with a dictionary, and these gauges has to has 2 yeah, well.